Okay, direct comparison. We have comparisons. We're going to use direct comparison and limit comparison. So direct comparison, we have two functions. Our series that we're calling B converges, and A is between B and 0. That means A must also converge. Okay, so we're going to compare this sequence to something that we know already converges. As long as it's less than, right? As long as we have this, that inequality, then it's going to be true. And then, of course, if one of them diverges, then the other one also diverges. But notice the comparison now. Here we have A. Well, B is bigger than A. Okay, we still have the same inner or inequality here. But now we're looking at A. If A diverges and B is bigger than A, that means B must also diverge. Okay, if I have $1 million and Joe has more money than me, then that means Joe has at least $1 million. Right? That's the lower bound of what's going on here. So the hard part is, to what are we going to compare this function? Okay, 1 over n cubed plus 1. What should we compare this to? Okay, so we're going to compare this to the sum of, right, so here's our notation, of 1 over n cubed. Okay, so here's what we have to remember. We need to have, so this is going to be our A, right, and this is going to be our B. So looking at the terms from A sub n and looking at the terms of B. So let's just think about, what if n equals 2? Then this becomes 1 over 2 cubed plus 1. 1 over 2 cubed plus 1 is 1 over 9, right? 1 over 9.
That's supposed to be a 3.
That's a 3. 2 cubed, yes, 3. It's a 3. It says it right there. Let's use our context clues rather than making me look stupid on my video. Over 1 over 2 cubed, which is just 1 over 8. So what fraction is bigger? 1/8 or 1/9? 1/8. Right? So we have this situation that we want. We have the A term is less than the B terms. Right? Because something with a bigger denominator is a smaller fraction. Okay, that's a really important thing to understand. If you have a bigger denominator, that means we have a smaller value or a smaller fraction. So what do we know about 1 over n cubed? Does this converge or diverge? This series converges. By what test did we talk about yesterday? By the P series, right? So the P stands for the power. Okay? So the power of the power of this function is 3. And 3 is greater than 1, right? And that was our stipulation, is that the power had to be greater than 1 in order for this 1 over in order to converge. So we know that 1 over n cubed converges by the P series. Okay? So now let's use our what am I going to call this? Our analysis. Okay, so how about our function? How does our function compare to 1 over n cubed? How does that compare to 1 over n cubed? Right? How does it compare? our function is less than or equal to. Okay, 1 over n cubed plus 1. This has a larger denominator, therefore it has smaller values. So if 1 over n cubed converges, then 1 over n cubed plus 1 must also converge. Therefore, the series also converges by the direct comparison test. Okay, how about this next one? 1 over 3 to the n plus 2. Okay. So our thought is that this is going to converge, so let's compare it to something that we already know converges, which I hope you know that this converges. 1 over 3 to the n power. Okay. 1 over 3 to the n. So this would be 1/3 plus 1/9 plus 1/27. Right? What are we doing to get from term to term? So these terms look like a geometric sequence. Okay, so can we write this as a geometric sequence? This would be 1/3 to the nth power, right? Because 1 to the n, well, 1 to any power is just 1. So this would be a geometric series with a ratio of 1/3. Okay? So what does our ratio need to be in order for our geometric sequence to converge? It has to be less than 1. Is our ratio less than 1? Yes, it is. So the summation of 1 over 3 to the n converges by the geometric sequence test. Okay, if we have a geometric sequence with a ratio less than 1, that series, right, which is the sum of all of those terms of your sequence when we add them all up, that series will converge to a single value, okay, by the geometric series test. So let's come back over here and use our comparison. So 1 over 3 to the n plus 2, how does that compare to 1 over 3 to the n? Right? It's less than. It has a bigger denominator, so it has a smaller value. Okay? Things with larger denominators, plus 2, anytime we're adding, that means we're getting larger. Things with larger denominators are smaller fractions. Therefore, the series also converges by the direct comparison test. And I'm sure you can write DCT, well, maybe not sure, but you can potentially write DCT, and that would be the initials of the direct comparison test. Okay, our third example, 1 from 4. Notice we're starting at 4 now, because we're taking the square root of 4, which would be 2. 2 minus 1 is 1, right? So we can't get a 0 in the denominator. So we're starting at 4 to infinity. Okay, we're adding up all of these fractions. So our thought is that this one is going to diverge. So let's compare it to something that we know diverges. And that would be maybe 1 over the square root of n. From 4 to infinity. Okay, it has to be that same bounds. We can't now start at 0 and go to infinity. We have to have the same bounds. Okay, so what can we say about this? Well, the square root is the 1/2 power. So we can use that p-series test again with a power value of 1/2. Okay, so this function diverges by the p-series test with p equal to 1/2, which is less than 1. So anytime we have a power less than or equal to 1, our series is going to diverge. It's going to add up to an infinite amount of value. It does not add up to a single concentrated number. Diverges means there is no constant, no infinite sum. Okay, so then how does 1 over the square root of n minus 1 compared to 1 over the square root of n? Which one is bigger? The thing with a smaller denominator is bigger. Okay? And minusing 1 means we're going to have a smaller denominator, because subtraction means we have less. Okay? So if 1 over the square root of n minus 1 is greater than 1 over n to the 1/2 power, then the series of 1 over root n minus 1 will also diverge by the direct comparison test. So let's look at the limit comparison test. Okay, so we have two positive functions, right? So they have to have positive values. There's no negatives in here. And if we compare these two functions, they have a limit, right? The limit exists where L is both finite and positive. So the limit of these two functions does not go to infinity, right? And it doesn't go to a negative value either. Okay, so we have some stipulations that have to be met. Then the two series either both converge or they both diverge. Okay, so they do the same thing. So we're going to have to, decide whether they converge or diverge, and then we'll do some type of a comparison here in order to find out. Okay, so what about this one here? What do we think? What are we thinking? Is this one going to converge or diverge? Right? Kind of hard to tell what it's going to do. But chances are maybe it's going to diverge. Okay, what's our highest power here? And what's our highest power there? N to the 4th over n to the 5th reduces to what? 1 over n. And what do you know about 1 over n as a series? Right? That's called the harmonic series, and the harmonic series diverges. Okay, this series 1 over n diverges. This is the harmonic series. 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh. Right? That's the harmonic series. All of those things do not add up to a single value. Okay? So we're going to compare this to 1 over n. Compare to 1 over n. So the p-value equals 1. 1 over n diverges by the p-series test. Sorry, that's pretty sloppy. So with a p-value of 1, this series diverges by the p series test, right? P equals 1, so it diverges. So this is going to be our a sub n, and this is going to be your b sub n. Okay, so this is how it works. We're going to take the limit as n goes to infinity of our a sub n, which was 1 over n, divided by your b sub n, which was n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7. Okay, so let's try and solve this, or algebra this out. I have a fraction divided by a fraction, which means I am going to multiply by the reciprocal. So the reciprocal of this would be 4n to the 5th minus n cubed plus 7 over n to the 4th plus 10. Okay, so then let's multiply here on the denominator, right? That gives us the limit as n approaches infinity of 4n to the 5th minus n cubed plus 7. There's your numerator. And the denominator is going to be n to the 5th plus 10n. So this limit of this rational function is going to be 4. Okay, all we have to do is use our pre-calculus, and notice that this is a neutrally heavy function. We have a 5th power on top and a 5th power on bottom. So 4 divided by 1 is 4. So that means it meets this right here, right? The limit, if we compare them, equals L. We're both finite and positive. Is our 4 positive? Yes. Is our 4 finite? Yes. It's not infinity. Okay. Therefore, the series diverges by the limits comparison test. Okay, let's do one more example here. We have the sum from 2 to infinity of 1 over n cubed minus 1. So this is going to be our b sub n, and we have to create an a sub n. So what is our other thing that we're going to compare it to? How about 1 over n cubed? Okay, how do we know about the sum of 1 over n cubed? Does that converge or diverge? Converges. This one converges to a single value by the p series, right? P equals 3, which is less than 1. P equals 3, which is greater than 1. 3 is greater than 1, therefore 1 over n cubed converges. So we're going to take the limit, and all this notation has to be there in order to do this correctly, of our function, which is 1 over n cubed. That's an m. And 1 over n cubed minus 2. Okay, so we have a fraction divided by a fraction, which means we have to multiply by the reciprocal. So 1 over n cubed times n cubed minus 2 over 1. Okay, and this equals, right, let's write this out, n cubed minus 2 over n cubed. So what is the limit, the horizontal asymptote of n cubed minus 2 over n cubed? Well, that's just going to be 1. So 1 is both positive and finite, right, which is exactly what our stipulation said. So because our A value, right, our A series converges, therefore the series also converges by the limits comparison test. So that's how you use a comparison test to decide if a function will converge or diverge. You have to know something about another function converging or diverging first before we can compare it to the one that we're given, which is the hard part. But you'll do great when you practice some more of these. I have the utmost faith and confidence in you. Okay, have a swell day. Goodbye.